coming up at my show. Every man in the crowd on the floor. Out of town, never saw her before. Tell her, baby, we don't got that long. Listen, this not my city show. But I treat it like my city show. 20 more minutes, enjoy more. 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 Enjoy more. 20 more minutes, enjoy more. I am not slow, because you want me, cause I got the dough. Pass that girl right on my shirt, you can go. Pass me her friends, so they switching roles. Yeah, I hit it fast, yeah, I hit it slow. Love by the morning, girl, I gotta go. You ready? Tonight is my show. You okay? You might help in my show. The big brothers right under my nose. These niggas mad 'cause I got out the dough. These niggas mad 'cause I got out the dough. My stuff 'cause I got every fly, got every girl, ain't no time for my hoes. Your girlfriend, bro. You know I got a kid for clothes. Be next and not keep it close. Been life on it, you're the type of. So clean up my stomach and so. Try to do Bobby, I don't even know. Try to do God like it's a bubble. I got your girl and you already know. Really like when we first the most. All right. Set up and ready to go. All right, so the first problem is going to be a problem that I got requested. Okay, let's pull it up. Let's close all this crap. Actually, let's keep the book open. Close this, close this. You know what I gotta say? This isn't an ad or anything, but Master Organic Chemistry is actually a really good website. Actually, I was kind of hesitant because most like study sites in that vein stink, but that one's actually pretty good. All right, so we're looking at this one. All right. Bro, I feel like this one's easy, is it not? You have CH3, CH, alkene to CH2. And you try to turn this into butane. So butane, CH3, CH2, pentane, CH2, C, CH, like this. Can we see it? Let me see. I need to do this thing. All right. So this is a pretty simple problem, I think. So first we're going to turn this into an alkyne. Oh, wait. Okay, I think I remember why this was hard. The issue is that we're going to get a non-terminal alkyne if we turn this into an alkyne and then do an SN2 using an acetylide ion. So that's actually not going to work. So how are we going to do this thing? Oh, let's see. What is the answer say? For T? Okay, so it says add an alcohol anti-Markovnikov, then add HCCNA. Oh, okay, yeah. Okay, what it's saying is, and then NABR. I don't know that reagent. So the one that makes sense to me is that they're saying instead of this, you're doing, BH3 in THF, and then you're doing, the standard H2O2 in with a base, and this is going to give us the anti-Markovnikov alcohol. So it's a hydration reaction. So we're going to get CH3, CH2, CH2OH. So 1, 2, 3. Okay, so that's what this is. Then they're saying tosyl chloride makes it a good leaving group in a base with B. This is how I like to write base. And then 4 is NaBr. So, okay, first, this is going to turn into O-tosyl. And then I don't know what the base does. I need to refresh myself on the tosylate thing. Okay. I think that let's just ask chat. What's the standard reagent set for tosylation of alcohol? It's pyridine. Okay, so then pyridine has two jobs. Oh yeah, because okay, yeah. So this could also be pyridine, because I think pyridine, is it like a 5-membered ring with a nitrogen or something, but this lone pair attacks it or something like that. But I think it might be more like a pyridine. Pyridine. Okay, so it's got the double bonds, so it's like this. Oh wait, no, it's hexagonal. Oh, for some reason I thought it was pentagonal. All right, so apparently this does what? Let's look up mastering ochem. Let's see. Tosylation. If a base like pyridine is added, it can act as a base here, speeding up the reaction. Okay, whatever. So I think a base is just needed in getting it in there. Because this oxygen attacks the sulfur, which kicks off the chloride. And then so this is step one, and then step 2, chloride comes in and attacks this on 2. So on 2, chloride comes in, and also a base like pyridine could also come and take the OH. Or whatever. You guys get it. All right. So that's chill. So the base is not anything else. The base is like part of the normal set of just getting that tosylate on there. Okay. Now this last step, step 4, is that they add NaBr. And my dude, there's no way that this makes what they're saying it makes. Because all this is going to do is you're going to have Na plus and Br minus. Br minus will act as a nucleophile? It's a primary alcohol. I don't see why it wouldn't just act as a nucleophile and turn this into... But now we just have bromopropane. Dude, I don't see how that works at all. That one's whack, dude. Not webcam, scene. Okay, so my book says that
With the HBr step? Wait, does this? Oh my gosh. It's so hard to remember all these. Wait, HBr in peroxide. Wait, hold on. Let's see the explanation. Yeah, okay. All right, so wait, hold on. So that's something that I just totally forgot about, is that if I take a alkene and add HBr in peroxide, ROOR, we get anti-mark addition of X, which is a halogen. So this is going to turn into Br. Okay, so that's what we get. That's one bromopropane. The key is a second reagent. Sodium acetylide. Wait, sodium acetylide. Oh. Wait, what? So then we have 1, 2. Wait, where's my fucking thing? I was wondering what the heck this is. I totally ignored this. So we're adding 2 carbons to it to get 5. So this HC triple bond, that was the key. So this thing is going to turn into acetylide ion in solution. So this is going to come in, attack SN2 on Br. Okay, I get it now. So this is the main thing. So we get this anti-Markovnikov addition of the bromine. Then the acetylide ion, which is this HCCNA thing. This turns into this in solution, presumably. And then we're going to get 1, 2, 3, 4, 5. But this actually should be like this, right? Because this is going to... No, wait, won't this be... Oh, it's going to be internal anyways. Okay, that's good. Okay, so that one made sense. I don't know what the hell this other tosylate thing is talking about. Oh, okay, okay. So this whole route is just another preparation for this. Okay, so I get it. I understand what the answer is saying now. This is a pretty cool thing. I don't know why you would go through this way. This is definitely the right way to do it. I forgot about this anti-Markovnikov halogenation. This is really useful. All right, that's good stuff. I like that one. Let's just keep doing these. These are really fun. I love these problems. All right, so problem U. Let me actually set up my phone so I can see if I'm in shot. Typically, that's what I do. All right, good shit. Now I can see. Okay, so U is... All right, so 1, 2, 3, 4, 5. So 2 pentyne. So 1, 2, 1, 2, 3, 4, 5. 2 pentyne into a racemic mixture of a syn addition. Let's see, that's interesting. Okay, so is this a... But it's not drawn as an alkene. So it's just whatever. Br wedge. OH wedge. CH3. So we actually have to remove a carbon. Right? Wait. Oh, I looked at the wrong one. Bruh. Okay, U. Et. Wedge. OH. Wedge. CH3. I think that this looks like, to me, let me think about it. It's probably some sort of epoxide thing, because in here we have this trans diol, and I'm pretty sure to get a trans diol you go through an epoxide, and I think just water or even a base could do it. But so here's what's going to happen. So we're probably going to reduce this with Linlars. Do we want to do Linlars? Does it matter? So in that case, it would be... And then what I'm saying is MCPBA. And then some sort of base, right? Can hydroxide act as a nucleophile? I don't know. But I remember seeing that water can do it. Base SN2s on the ring, but yeah, we can use, Grignard reagents. We can use just to attach another R group. We can use, here we go, here's the hydroxide. All right, so we can just use a hydroxide to do it. That's what I thought. I mean, that makes sense. Okay. Let's see, I want to do something here. Okay, that's good. So all right, so then we're gonna add NaOH and OH minus. Okay, and wait, we need to think about this. I think these typically attack the least, right? The epoxides get attacked at the least substituted. Oh, yeah, okay, I forgot about this. In basic conditions, epoxides get attacked at least substituted. I think in this case it actually doesn't even matter, but I kind of want to know where the mechanism. So it's NaOH, NaOR, NaCN, an acetylide, a Grignard. Is Grignard considered a basic reagent? LAH? Does LAH? I guess it's... Most of these reducing agents, yeah, are basic, I guess. Okay, but in an acidic condition, the epoxide oxygen is protonated first. Oh, okay. In acidic, we do this thing. But the thing here is, like, let's say that this is substituted and this is just H's or something. Then the problem here is that we're going to get this is kind of almost like a carbocation because it's taking so much away from it. So this is more stabilized. So obviously, this one's not going to open up. So then, OH or some sort of base will come in here like this. Okay, but in our case, it's a basic condition. So this is going to come up here. It's going to go there. So then we're going to get the... Oh, wait. I don't think this is right. I think we did it wrong. Because... this should turn into... But actually, if I spin it, does it fix it? I need to figure that out. If I rotate the bond, does it turn into... Or, well, but, oh, we need to add acid afterward. Okay. So I probably got it right. So, wait. Oh, interesting. Oh, what? Wait. First, it made a trans alkene. So I was already wrong about that. So first, what happened is it went to Na and NaH, NH3, sodium and ammonia. And that's going to give us the trans alkene. Okay. Then, so this is the first step. Then the second step was just KMNO4, which KMNO4 and an alkene. What does KMNO4 do on an alkene? Let me open up my alkene spreadsheet. I really should have been adding to this all along, but I didn't. Sin dihydroxylation. Okay. It adds sin though. Cold dilute KMNO4. Okay, yeah, I forgot about this. Potassium permanganate is a really weird reagent. All right, so apparently this does sin dihydroxylation. So, but I want to think about the stereochem because I have to do it like this. I'm kind of dumb in this way, but if this is going back and then this is coming out at me. All right, so this is the same thing. This is just drawing it in a plane. So these H's are coming at us. These are going back. Wait, is that right? I don't think that's right. I think I messed this up. Yeah, this is obviously wrong. Okay, wait. I gotta wake up. I'm slow right now. I'm so bad at drawing. Okay. Anyways, this is the right one. Don't look at that one. So these are coming out at us, and this methyl group. Let's do this. So what it's saying is that we're gonna get what is that? Oh. All right. So is this what we wanted though? I guess it is, right? Because if we permute these, I always have to look at it if we're gonna like. I'm so dumb that I have to do this. So OH. So we're looking from over here and we're looking at this thing. CH3H. Oh, and I forgot actually how to do these projections. The one in the back, I always forget if it's the one in the back or not. OH. H. Yeah. Okay, the one in the back I'm saying is from the ring, and the one in the front is in the center. Okay, and what I'm saying is I want to rotate this outer one. So I'm going to rotate this. So CH3, because CH3 and ET are already across from each other. So that's why I don't understand how this works. Are we allowed to look at this? Like, but this is not an alkene. It's not planar. So I don't know what the deal is. Okay, I gotta. What are these things called again? These projections? I forget what they're called, but they're very useful. All right, instead ask, are the two hydroxyl groups on the same face in this particular drawing or opposite faces? No. Okay, actually this is right. This is good. So in this case, the hydroxyls are both going to be in the plane of the sigma bond. And they're going up and down, just like in here. So that's good. And then here, et is up, and methyl is down, and they're both, in this drawing, going into the page, if you were looking from here. But you know, you could look from here, and it's there. So I get it. Okay. A little stereo chem to get the mind working in the morning. Okay, so this one was but okay, so now the question is this probably won't work, or are we allowed to, does MCPBA work on a, presumably it comes in from the top, so we can. So what I'm wondering is, instead of doing this, because I think that this probably won't work, is if we, because the problem here is if we draw this, so we have an so let's just draw the H. All right, so we're looking at this thing. So we have OH, H, CH3. And then here we have an OH, an OH, H, and an ethyl. So if we put the hydroxyls, you know, nope, can't see it. If you put the hydroxyls such that, let's do this, shift it, so this is OH, so et is here. Oh wait, no, et's not there. CH3 is here. H is here. The et is here. I think this works. Does this not work? Am I wrong? Okay, it's saying no, that this is not right. So okay, you know what? I can kind of see that. I don't know what the hell happened that was wrong here. This is no good. Oh wait, I gotta switch it to auto. If I do auto, will it start to do the white balance correctly? That's actually worse. All right, I'll just have to modulate it. That's okay. I'm fine with that. That's better than having to deal with the other way, where it sucks. Oh, I have to do it here. All right, that's fine. So I don't know what the heck happened here, but we can't spend all day on this. So the main thing to remember is that cold dilute potassium permanganate does a syn dihydroxylation. All right, that was a tricky one actually. That was pretty good. Man, this reminds me of last quarter, dude, doing all that math. That was fun. All right, the next one is V. And V is, we're going to take one bromopentane. So, and we're going to turn it into 1,2-dibromopentane. All right, so this one's easy, right? I think this one's easy. So what we want to do, so this is going to be, so I think we want to turn this into an alkene. And the way that we're going to do that is with a, I don't know, methoxide or something. Some good base that comes in here, pops this one off, and then comes in here. Oh, wait. Hold on. Hold your freaking horses. What's actually happening here is it not this? It's, the base comes and takes this. This is what I should have just done on the iPad. Maybe it is better if I just do auto. I'm just going to do auto and live with it, because I can't keep messing with this thing. Okay, so all right, so that's what it is an E2 mechanism. And then we just add bromine gas. I should review stereochem because that is the I think that's like one of the most interesting things in chem is stereochemistry. All right, let's see if I was right. Yeah, it added potassium T-butoxide and heat. Oh yeah, I forgot the heat. And then bromine gas. I mean, I feel like that's fine. All right, W. So we're getting 2-butyne. And we're turning it into Like this. I think it's just going to be H2 Lin Lars, and then that's going to give us. And then we're just going to do. I think it's. Yeah, it has to be Br2 in water. I think that's it. Why does it say racemic? Oh, it is racemic. Yeah, I get it. All right, so I think that's it. W. Oh. Oh. No, because here, look. Think about this. Think about this. I'm playing fast and loose, and I gotta lock in because exam is today. Here's what happens. Okay, we get this thing, and this is sin. We get the BRs, but now water comes in. Let's have it take this one, and it's gonna do this. Boom. That's no good. All right, so lesson is every time you see a wedge, you got to pause, put the pen down, and think about it. Because if instead we had done this, we turn this into, Na, NH3. That's why I like always just drawing the mechanism. Okay, so wait, what I want to do here is I want to do this. Okay, then we're going to cross this guy out and we're going to put BR here. And then we're going to have water come in from the bottom. And so then we're going to get yeah. So if I flip this, so I want to do this. No wait, I fucked this up. Let's fix this. Okay. So we have Br, CH3, and H. Oh, this is H. Oh no. Fuck. This is H. This is CH3. Okay, and then out back we have H, CH3, OH. Now, if we flip this 180 degrees so that these guys are aligned, dude, I must be doing something wrong with these projections. Oh, wait, no. This is the correct case. This is the correct case. So if I rotate this 180 degrees, not the best. Okay, so then we're going to get BR, OH, CH3, CH3, H, and H. So everything lines up. But if we were to do this here with the syn one, we would not get that. All right. Nice. Let me get some coffee. I'm back. Let's see, what time is it? How much time do I have? Damn, it's already 10. Okay, I only have 2 hours left to study. Fuck. Okay, all right. All right. So we can't. What are these projections called? They're not called gauche projections. What are these projections called? Where you look down a carbon? Oh, Newman. Yeah, Newman. Very useful. Very useful. I really like the Newman projection. All right, that's good. So next one. So we did W, and it turns out I'm just getting everything wrong today. So, all right, X. We're turning one butine into pentanal. Interesting. Okay, this one seems pretty fun. So we're gonna get C, 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 H, whatever, H2, H2, H3. Okay? And we're turning that into one. Wait. Oh, yeah. 1, 2, 3, 4. Okay, yeah. So this is butanal. Butanal. And butanal. Okay, so here's what we're going to do. I think it's just one reagent. And I think all it is 9 BBN. Probably in like THF. And then I think the next stuff is just, peroxide and an AOH or something. I've just memorized this. I don't even know the mechanism. But yeah, that was right. That's it. To turn a terminal alkyne into an aldehyde, you use this 9-BBN thing. My book says just use BH3, but my professor told me that stuff doesn't actually really work. So, whatever. Yo, Lemon Leaf is here, bro. What's up, Krish? All right, so okay, this is a good one because I feel like this is really powerful to get an aldehyde, but I think how do we turn? Now I want to know, how do I turn a terminal alkyne? I got to review some of this oxidation reduction in bulk, because how do I get a carboxylic acid instead? Okay, so I see here that I can use, a 9-BBN to do this. Okay. I see I could use 9-BBN to turn terminal alkyne into. Sorry, bro. It's exam day, and exam day stream etiquette goes out the window. Let me tell you. All right, so to turn terminal alkyne into aldehyde, but how do I turn the terminal alkyne into oic acid? Is that what it's called? Yeah, it's called oic acid. Dude, I hope you're well too, bro. I'm crushing exams. I'm living life. I feel great. The only thing is I wish I had a little bit more time to do fun stuff. But, it's chill. It's only 1/4. Use oxidative cleavage. Oh, yeah, okay. Right. Okay, so if instead, that's why I need to look at those star charts. The star charts are the best. I probably need to do a little bit more memorizing. But if I wanted to turn this into, what we could do is, yeah, we could take this thing, we could cut it right here with O3. Wait, does O3 do it? What does O3 not do? Okay, bro. Nice. Have a good one, man. For alkenes, the difference matters a lot. Okay. So the main thing is that O3 in alkenes um stops, it cleaves, stops at aldehyde. But so that's where you have like something like this, like C, and you just put little O's there, so it ends up being like, and then it attaches to H. So, but hot acid KMNO4 will go all the way. But in the context of thanks, man. In the case of this, in the case of alkynes, though, they do the same thing. Okay, good. All right. Yeah. So in this case, it's O3. And is there other reagents that I need to write down? Yeah, so it's 1 O3. For alkyne O3 ox, what's reagent set? Oh, it's just that and water? Because so you don't need to do this reductive workup zinc and acid thing, or sulfur, dimethyl sulfide or whatever. Okay. All right. I hate memorizing that stuff. I like the puzzles, but I don't like the memorization. Okay, let's do Y. Let's see, how do I... Okay, so I'm going to put up a stick here. Okay, so Y is acetylene into... Ooh, what the hell is that? That's some weird epoxide. So, 1, 2, 3, 4. So wait, I want to practice naming these. So I think it's just going to be... Oh, how do you name this? I know there's two different ways. You could do this oxyrane or something like this. I don't know what the hell that's about. But presumably you just do this. You do 1 ethyl, 1, 2. Oh, wait. Actually, I don't think you can do that. I think you have to do 2 ethyl. Because it's going to be epoxy butane. So maybe it's 2 ethyl, 1, 2 epoxy butane. Where's my mouse? I can't see anything. It's too bright out. Two ethyl, 1, 2 epoxy butane. That's what I think it's called. I think it's called 2 ethyl, 1, 2 epoxy butane. Oh yeah, you don't even need to. Yeah, no. See, I'm confusing them. This is all that you need. I'm confusing the two naming mechanism. 1,2 epoxy butane. Or 2-ethyl oxyrane. Okay, I got it. All right, so anyways, let's convert this thing. So I think it's just going to be NaNH2, then in NH3. Then the second thing is just going to be not ethidium bromide, ethyl bromide. And then we're going to get, so now we have butane. And now, does it matter? Is there any stereochem that matters if I just do H2 Lindlars and we get, no, it doesn't matter because this is terminal anyway, so it doesn't even matter. So we're just going to get, that's it. And then, now, just MCPBA. Let's see if I got it right. Okay, NaNH2, ethyl bromide, Lindlars, MCPBA. Bam! Yo, the alkyne stuff I low-key got, man. Let me get my hat. All right. Okay, so now we're on the last one of this whole thing. And then we're going to go probably to, well, I'll probably read her notes, I think. That makes the most sense. Okay, so, this last one is again, HCCH, which is just, ethine. I prefer ethine over acetylene, but acetylene sounds cooler. Okay, and then we're going to get 1, 2, 3, 4, 5. We're going to get pentanol. So, ethine, pentanol. Oh, this seems like a good one because, so obviously we're going to turn this into, so, NaNH2 in NH3. Then we're going to get, we're going to add bromopropane. And we're going to get, no, it's not like that. This. 1, 2, 3, 4, 5. Okay, now we have 5 things. And now, I think we can just use Lindlars, H2 Lindlars. And then all we have to do here to get an alcohol is add BH3, THF, H2O2, and AOH. Add the anti-Markovnikov hydration. So I feel like that's it, right? Let's see if I got it right. NaNH2, propyl bromide, Lindlar's catalyst, and then, yes. Bro, I'm, like, getting good at this. I love this stuff, man. This is so cool. Chemistry is so fun, dude. I actually, like... I feel like the way that... I feel like I could teach chemistry really well. Like, firstly, if I were to teach someone chemistry... I would probably start with organic chemistry and not general chemistry. I feel like general chemistry is like pretty stupid. Like maybe in high school, but in college you should start with ochem and then go to to general chemistry, or like general chemistry will come up naturally in the study of ochem, but like Gen Chem, it's just so many random ideas. It's like, bro, what are we doing here? Like, like if you're gonna talk about Gibbs free energy, why don't we talk about Gibbs free energy in terms of stuff that's like important? But also, like, I'm definitely of the mind that structural biology, or not biology, structural chemistry and like conformational and stuff where you're really looking at like a single molecule and saying, okay, like, why is this behaving the way it is? And it's a much more natural place to talk about, you know, trigonal planar and all this random stuff. And it's like, I don't know, geometry and stuff like that. But I just wish like my OChem, like I had great teachers, but I just, the ordering and the way that like, if I were to teach chemistry, I would start off by being like, I would want to show a lot of animations of like simulations of like ethane spinning around its carbon-carbon bond, and then showing that in a steady state it settles into the gauche or whatever, the staggered and stuff like that. But like, I don't know. I guess they did a pretty good job. I just feel like you got to start off ochem. I would also start off ochem with like some big synthesis problem and say, okay, here's some examples of people making and synthesizing like really big molecules, and this is like what you're going to be doing. Like this is the bulk of what ochem is about, is synthesis problems and mechanisms. And I would just like the first day of the class, I would just go over that and be like, okay, this is what you're in for. And then I would go over more conventions. Like I remember I was in my either my first or I think it was in my second ochem exam, and the professor had written this one, reagent, two reagent, and I was like, we've never even seen this before. Like, does this mean that you're adding them at the same time, or you're doing two different steps? And he told me, which is nice. But I was like, so I would go over conventions and stuff like that. But I would definitely talk more about like the relevant parts of it. Like, okay, hey, this is what you guys are going to be doing for the next year. And before we can get to this, there's some important stuff about geometry that we need to talk about. And then you get into stereochem, R's and S's, and the, what is it, the Kahn-Ingold pre-log rules, CIP rules, something like that. Anyways, and chair flips and all that stuff. But I just wish it was just like something that like nobody told me, and you kind of just picked it up. But it's like it would have helped me so much to have that in the beginning. Okay, enough of that. So now I think I'm gonna just switch over to the screen, and we're gonna go over. I'm gonna go over her alcohol notes. And just see if there's anything I'm really missing. And if there's not, I'm just going to go to the textbook and do a bunch of problems. Because I feel like problems are really the best. I mean, how many times do I have to say it? But problems are the best way to do anything. Because then you really got to, like, then you really got to think. If you're just reading notes, it's like, what are we doing here? Okay, so let's switch this thing over just for a little bit. All right, so this is the first one. Is this alcohols one? No, this is the second set of notes. Okay. So alcohols are basically like water. They're sp3. They don't have to be sp3, right? Do they? Actually, I think she did say that alcohols are specifically sp3. So you couldn't have like oh, but this would be an enol. Hmm. Okay, so anyways, okay, so yeah. So the thing is like, okay, you could try to come up with some. Now actually, could you get a SP? Let's see. What happens if you did this? That would be weird. So I alcohols are specifically hydroxyl on sp3 carbon. I see that if we had a CCOH, that's enol, and it tautomizes. But could we have C-trip COH? Oh, I should be writing the hash. I should get better at this. I always write trip, but hash is the way that they do it in Smiles. You can draw something like that. Enol. Ooh, so this is called an enol. Yeah, that makes sense. Very unstable, and they tautomerize quickly. What do they tautomerize to? Oh, a ketene, bro. Ketene. Oh my gosh. So ketene is super toxic, I think. Um. So this is a ketene, and it turns out that ketene is used in the production of acetic anhydride. I don't know if that's industrially the way that they do it, but I have seen a video where they use ketene to synthesize acetic anhydride on Doug's lab. Interesting. So inols tautomerize into ketenes. Not a ketone, but a ketene. Very cool. I forget the mechanism and the reaction to actually make the ketene, but and how that makes the acetic anhydride, but still really cool. All right. So wait, let's let's just keep going. Yeah, so alcohol, enol, phenol, methyl salicylate. We've made this a number of times on this channel. Failed one of them, made it twice. Made it from salicylic acid and from aspirin. So that's pretty cool. The industrial preparation of methanol, the simplest alcohol, is some crazy high temperature thing. You can make a. So I've done this on this channel too, fermenting sugar into ethanol. That's pretty good. There's no way we need to memorize this. Phosphoric acid. If you heat up this thing with phosphoric acid, you can get ethanol. So ethene, hot. What happens? This gets protonated carbocation, and okay. So actually, no. This is just standard stuff. It's just acid catalyzed. So the ene attacks a hydrogen. Then we get a carbocation. Okay, then water comes in, and then you get, OH, basically. Okay, fine. Ethanol. Okay, then yeah, we get the substitution, just like carbons. Naming. Diol naming. Benzyl alcohol, T-butyl alcohol, ethylene glycol. Can't you just call this 1,2-ethyl ethane 1,2-diol? Let's see, PubChem. Ethane 1,2-diol. Yeah, so you can just call it ethane 1,2-diol. Triol is a glycerol. Allyl alcohol is an alcohol whose carbon is adjacent to a double bond. Meta-methylphenol. Okay. Wait, meta? I thought this was ortho. Oh, wait, no, wait. I think this is wrong. Wait. Ortho, meta, para. Yeah, dude, what? She wrote the wrong thing. Didn't she? Dude, she wrote it backwards. Right? Yeah, ortho is next to meta is... Yeah, right. She wrote it wrong. Okay, this is wrong. Meta is down here. Ortho is next to. Para is obviously right. Okay, yeah, we get bent, tetrahedral. Yeah, we get oxoniums. Yeah, we can deprotonate it to make an alkoxide. Oh yeah, this is good actually. Okay, let's think about this. So so alkyl substituents on an alcohol are electron donating, which means that this thing is pretty stabilized. This oxygen because what you got to think of it. Okay, imagine this is deprotonated. How much can we stabilize this extra charge? Not really, because it's donating these other substituents are donating density into into the CO or into the C. But so look at a case like this. This lone pair gets sent into here all sorts of ways. Alcohols being weak, acids, they will only react with alkali metals. NaH, sodium amide, Grignard reagents. Okay, I don't even know what we're talking about here. The alkoxides are bases. Yeah, we learned that. Phenols are more acidic than alcohols because their conjugate base is resonance stabilized by the ring. Okay, this star is pretty good. I'm down to watch this star, or look at this star. All right, so this is an ester, carboxylic acid, alkene, ketone, aldehyde, ether, alkyl halide. So we can make alcohols from all of those things. All right, so let's first start with hydration of alkene. Yeah, okay, so we have 3 ways to make alcohols from alkenes. We have more than that, but for just adding 1 OH, no, there's 3 ways to hydrate it. Yeah. The other things are like diols. So here, first we just add acid. an acid will do what I just wrote down. It'll basically, the alkene will attack a proton on the acid to make water and a carbocation. Then water again will attack the carbocation, and then another base, either conjugate base or water, will deprotonate the attacked water and form the hydration product. The other thing you can do is you can add mercury acetate, and there's probably a bunch of other stuff in there. I always forget. Mercury acetate. Oh, it's just mercury acetate and water, and that gives you the Markovnikov OH or hydration. And then to get the anti-Markovnikov hydration, you do BH3, THF, H2O2, and AOH. Okay. So that's chill. Diols, osmium tetroxide. Yeah, and then we can do epoxide. Um, yeah, so we have two ways. We can make a trans diol or a cis diol. Cis diol is through osmium tetroxide, and trans diol is through MCPBA or some sort of peroxy acid. Right, that's chill beans. Okay, reductions. I'll be back. I gotta go get some more coffee. Okay, so what are we doing now? We're gonna be doing structure and properties, acidity, substitution. Bro, I feel like this exam can't be that hard. All right. Let's see. All right. So let's just keep going through the notes. Wait, where did I put my hat? I lost my hat. All right. So the preparation of alcohols. Oh, that's interesting. Wait, how do you take RX to ROH? So let's say we have CH3Br, and we want to make CH methanol. Okay, fine. Okay, yeah. So it's just like for a primary, we're just gonna add NaOH, and OH just comes in and SN2s it. But then if we have like a tertiary, so we're gonna have CH3 3CBr. Then we're gonna do plus H2O. So first this just goes here, SN1. And then H2O deprotonates it. Okay. Fine. If that's the way it is, that's the way it is. Okay. Adding to alkenes, yeah, we know these three ways. All right, this is kind of the stuff that I was more interested in getting into. Reduction of aldehydes and ketones. Is there a formula? Oh shit. Okay, I'm glad I'm looking at this because I don't remember this at all. What's the carbon oxidation state formula? Assign electrons in each bond to the more electronegative atom, then count carbon's charge. Okay, yeah, so... Alright, so if we have CH, CH, H, Cl, Cl, dichloromethane, then we're going to have plus 2 minus 2 equal to 0. So DCM so CH4, yeah, so CH4 will be reduced to minus 4. Methane is reduced. Okay, I'm glad that I'm running into this because I would have forgotten this. Yeah, so then CH3OH will be 3, or it'll be 1 minus 3 equal to minus 2. Formaldehyde is going to be minus 2 plus 2 equal to 0. Okay. Formic acid. Okay. All right, good. All right, so that was a good review. I don't really feel like that stuff is that hard. The main thing is, yeah, reduction is reducing the oxidate, is lowering the oxidation state. So this plus 2 would change into a plus 1. So this would be plus 2 and then into... But you also have to add a hydrogen to the thing, so this has to be 2, 0. So this changes by 2. Okay, yeah. Right, okay. This is something that I need to remember is the sodium borohydride reduce an alkene. Oh, apparently this reduces carbonyl. Wait, okay, yeah. We need the hydride to be a good nucleophile and not function as a base. Sodium borohydride will not reduce esters and carboxylic acids. LAH stereochemical outcome same as NaBH4. It seems like NaBH. It seems like sodium borohydride is not stereospecific at all. Wait, is this right? Okay, so a aldehyde. Where's an aldehyde? LAH and sodium borhydride both give a primary alcohol from an aldehyde. Okay. And then in the case of an ester, what happens to an ester? Do you have an ester? Yeah, an ester. An ester also turns into a primary alcohol. Wow. So then we should get methanol out of this, right? Oh. Yeah, no, wait, what? Wait. No, yeah. Okay, it doesn't give the aldehyde, it gives the alcohol. Okay. All right, I get it. But it does give methanol too. I feel like Grignard and acetylide are pretty straightforward. Is there anything I need to know about Grignard? You just add magnesium, right? The chain, oh, the delta electronet, yeah. Okay. Grignard reagents are carbon nucleophiles that can attack a wide range of electrophilic centers, such as the carbonyl group. Similar to LAH, we need to keep water separate. Grignard is also a very strong base that will deprotonate water to make irreversibly that will destroy the excess Grignard reagent will also react with esters, but not carboxylic acids or even mildly acidic protons. You need to protect the alcohol. Bro, she didn't talk about the alcohol protection. We did all this, right? Okay, good. Oh, the first thing she started off with the protection thing. Okay. BROH protect, then Grignard, then deprotect. Okay. OTMS. Okay, so okay, so protecting groups. So let's say we have an alcohol ROH. We're going to add TMS chloride. And we're adding, what is this solvent, dude? Triethylamine? triethylamine. Okay, whatever. And this is going to turn this into ROTMS. So just like the tosyl chloride, it's a useful reagent to look at this mechanism, man. Oh, so you could probably use pyridine too. You probably don't need to use a triethylamine. You probably use pyridine. So bam, boom, bing, bong. Oh, actually, wait, it's like very similar to. All right. Okay, so yeah, so let's do a real example. So Br OH. Then we're gonna add TMSCl in, I don't know, pyridine or something that has like a basic nitrogen or something. I don't know. Anyways, it's gonna go BrOTMS. Then we're adding magnesium to it. So first magnesium. So then we're gonna get BrMgOTMS. Then we're going to do our actual Grignard reaction, and we're reacting with this ketone. And so this carbon is going to come in here and attack this and push onto here. And so what we're going to get is this carbon now has an O on it, an R on it, and another R. Doesn't this have two H's though? How does that work? No, because we're adding a carbon. So we have this C with H and H, and then another C down here. And then we're going to go to this C, which has R, R, and O. Okay. And this is a minus. And then something protonates it, I guess. Water protonates it. There you go. Yeah, so now you have 1, 2, 3, 4, 5. Wait. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. Okay. All right, then TBAF is the D protect. Okay, so this thing becomes. So then TBAF D is the D protect. Oh wait, is it? Wait, what is this thing? TBAF. Okay. Oh my god. chat. Hold on. I'm going to it. Wait, hold on. Yeah, you have to protect the OH before the Grignard. Oh yeah, it says right there. TMS seal. I love the hat. You can use TBF or acid. Yeah, that's what I think. Yeah, you can use. Yes, I agree. That's where the F minus comes from, the fluoride ion. And fluoride. Yeah. So okay, so that's good. Let's keep going. I feel like this is chill. I'm just gonna use acid, bro. I'm trying to minimize the number of reagents. I want to minimize the number of reagents that I have to memorize because there's so many reagents. All right, this one's pretty chill. SN1. Tertiary alcohol does SN1. SN2 on a primary or a secondary. What is this zinc chloride here? I don't know what's up with that thing. Tosyl chloride turns it into a good leaving group. And because it's SN2, you get an inversion. All right, here's the structure of the tosylates. Here she wrote it right. In the last lecture, she wrote it wrong. Okay. Propanol. Oh wait, I need to check this out. Okay, so these ones are just ways to make alkyl halide from alcohol, and they're just like convenient ways to attach. All right, so. All right. Yeah, so these reagents I gotta remember. Easy way to add or to get and I wonder, does this require it to be like primary? She didn't really say much about this. Easy way to get a alkyl halide from let's say primary alcohol. And what we do is let's say we have like propanol, we can react it with this thing SOCl2. Well, what is this called? What is SOCl2 called? Oops. Thionyl chloride. Thionyl. I don't know how you name that thing. Chloride. And this just takes it. All right, we're done with this one. Okay, the other thing we can do is we can react it with what? Tribromo or no, phosphorus tribromide. How do you call this? PBr3. Yeah, phosphorus tribromide. And this similarly does basically the exact same thing, except it gives it bromine. And I'm pretty sure that bromine is a stronger leaving group than chlorine, and then iodine or iodide is the best of the halogens in terms of leaving group. All right, so strategy for SN2: convert OH to a good leaving group. Yes, you could use but I think the no, so you're gonna get inversion no matter what. Yeah. Tosyl chloride. Yeah, okay. What did we call this? Thionyl chloride? That's a weird name that I'm never going to remember. Why can't you treat it with HCl? For which one? Wait. Okay, wait. So I think what you're saying is propanol in HCl. So let's see. Propanol, HCl. Okay, so this is going to take this. I think what happens is that, so we're going to get the oxonium. So we're going to get OH2 on the end because it took a proton. And then Cl. Yeah, I don't know why you can't just do this. Let's see. The only thing I can think of is maybe that because no, I don't know why you can't just do that. That makes sense. I'm reading about making alkyl halide from primary alcohol, and we have TOS chloride, SOCl2, PBr3, but why doesn't just normal HCl work? It seems like it would. Hot the OH to oxonium, then Cl minus SN2s. It's often slow and inefficient, while plain HCl is weak for primary alcohols. Chloride is not that strong a nucleophile in water. Yeah, because see, I was thinking like maybe if it was like a tertiary alcohol, it would be better because then you would protonate the water into oxonium, but then it's a great SN1 leaving group because it's tertiary, and then chloride could come in. So maybe that's why. Yeah, I think it's the primary thing. Yeah. Yeah, but okay, wait, but same reason for HBr. We just uh low could we do for for some alcohols, especially tertiary alcohols, HCl works fine. For primary and secondary, you kind of need. Oh, there's some other reagent we don't know about. I don't think we ever learned about Lucas reagent. Okay, so I'll probably just remember those because I feel like we already remember tosyl chloride and these thionyl chloride and phosphorus tribromide are pretty chill. All right, so specifically primary alcohols, we gotta think about something else because, but so couldn't HBr. Wait, is Br a better nucleophile? Same basically, but HBr works better than HCl because Br minus is a better nucleophile and is less strongly solvated. Okay, I mean, yeah, I don't know. I don't really know. I feel like HBr would be totally fine in this case. Oh, but also, okay, yeah, wait. The other thing is, with acid, with like HBr, we get a carbocation. Wait, do we? Or is it SN2? No, yeah, it's wait. Wait, do we get a carbocation? We don't get a carbocation. For a primary or secondary alcohol, just use the PBr3. For tertiary, you want to use, okay, so specifically tertiary alcohol, we want HBr. Alright, I mean, I guess. Strategy for SN2. Convert OH to good leaving group. Oh wait, we already went over this, didn't we? E1 and E2 type reactions, eliminations. Alright, so sulfuric acid gives us Did she draw this right, dude? Alright, so okay, so in this case we have this tertiary alcohol. And we're adding H2SO4 with heat. I need to see a mechanism there, because what I would expect to happen is first, the most obvious thing that happens is that we protonate to oxonium. Then I would guess that some conjugate base takes a beta hydrogen and kicks off the water or something like that. So then we get, okay, I get it. Yes. So that is exactly what happens. All right. This is correct. All right. So another way to do it is we add TOS chloride and then we get OTS. And then we add some really strong base. Strong base. So like sodium ethoxide. So then we have, you know, an E2 type of thing. So this O comes here, pops this, pops that, and then we get the same thing. Oh yeah, and also Zaitsev. Do they both Zaitsev? Presumably you can tune the base here just like normal to get Hoffman, but yeah. Okay. All right, oxidations. This one I wanted to get into. The problem for me is always remembering what the hell, like what takes it to. Okay, I only got like 30 minutes left before I really got to clean up and go to school. Dude, ochem is like the best, man. Physics was the best last quarter. Ochem is the best this quarter. So if we were to think about the oxidation state of this thing, we would have a +1 here and a -2 here. And then the R is a 0. So this would be, is that right? -1? I feel like they were always in numbers of 2. Yeah, so for a primary alcohol, the ox state is -1. So then you go here and you get +2 -1. So you get +1. So then aldehyde, Okay, good. Oh yeah, okay, so you can't oxidize a tertiary alcohol, but you can do it once for a secondary alcohol. All right, reagents. Oh, I don't even remember this. All right, I'm glad I'm reading this because I don't even remember this. Chromic acid. Okay, so PCC. Okay, I don't remember this one either. Pyridium chlorochromate. Okay, wait. So PCC takes primary alcohol to aldehyde, and what is it called? Sodium chromate. Sodium chromate. That's different. What is this called? Jones reagent. Wait, Wait. Oh, that's Jones. Wait, is you're saying sodium dichromate is also called Jones? Okay, but both take primary or okay. Okay, so PCC takes primary all to al to an al, and sodium dichromate slash Jones takes the primary all um to an oic acid, to the oic acid. All right, that makes sense, I guess. Oh, DMP also does this. So PCC or DMP. So PCC or DMP do the same. Okay. It's so hard to remember the reagents for this, I feel like. I think it's the same. Jones or sodium dichromate. They both. I'll just write Jones. I need to do some practice problems. Okay, so the problem with these reagents is if I don't even know what they look like, I have a very hard time remembering just based on the name what the hell they do. But they both take a primary all to an al. And Jones takes primary all to an oic acid. All right. So they're both, these are all oxidizing reagents. So we're talking about oxidizing alcohols. Swern? Wait, what? Oh, so Swern is also like PCC. What is Swern? Okay, so if I have a secondary all, just use Swern, which is dimethyl sulfoxide, I think it's called. And what is that? COCl2 in triethylamine. And we get a ketone. Dude, I am not going to remember all this stuff. Oh, what is this? I don't remember this. Bromine gas, light. What is that? UV light or something? And methoxide gives us a. All right, I need to look into that. So we can actually take an alkane and make a alkyne. Okay. That one's pretty interesting. And then here, Br2, and then just base it. Yeah, that's chill. I love these graphs. These graphs are so beautiful, man. Like, think about what this means. It's so amazing. This is two steps, right? First, we're gonna add like either acid. In this case, acid's fine, but you could add mercury acetate, or in this case, it doesn't even matter. You could add borohydride or whatever it's called, BH3 and THF, the whole thing. And you would get an alcohol, you would hydrate this, then you would add, so hold on. So we want to make a ketone, so we're going to add Swern. Is that what she adds? Okay, we can also add Jones is strong. So Jones can also take a secondary. So wait, let me just ask, what's what's the most common reagent to take a sec all to? Oh, I think it's gonna mess up. I need to put a dash there. Oh, there we go. It got what I was. PCC. Wait, does PCC work? I'm gonna say Jones. I think Jones is the right one. So Jones is 1CrO3 in H2CrO3, H2SO4, and then H2O. This is Jones. I'm not gonna remember this, dude. So many oxidizing agents. So many. Oh, I forgot about that. See, that's the problem is there's so many routes. Oh yeah, because you're okay. Yeah, yeah, yeah. Wow. Okay, this is pretty neat actually. Yeah, so you could form the alkyne, and then you could do the mercury sulfate route, which um takes an alkyne to an enol, which tautomerizes to a ketone. Got it. All right. Okay, I'm almost at the end. All right. I'll be right back. All right, let's look into this UV light thing. I'm actually curious about it. Uh, how do we turn an alkane into alkyl halide? I think my prof said something like Br2 in UV light. Yes, the standard way is free radical halogenation. There's no way she's asking about this. Dude, if that shows up in the synthesis problems, yeah, I'm low-key kind of cooked. Because, like, synthesis problems are just, let's see, I want to review this again. Let's see, what do I know? Yeah, acidity of terminal alkynes, that's chill. I mean, I don't know what exactly the pKa is or anything, but I know that you can use them. They're strong enough that you can use them as nucleophiles. Or that you can deprotonate them and then use acetylize as nucleophiles. Partial reduction of alkynes, that's just Lindlar's, Na and ammonia, and H2 palladium on carbon. Oxidation of alcohols. Okay, so we got a lot here, and it's becoming apparent to me that I overestimated my ability with alcohol oxidation. Okay, if we have a primary alcohol and we want to turn it into an aldehyde, then we want to use PCC or Des-Martin periodinane, DMP. If, however, we want to turn that into an carboxylic acid, we are going to use Jones reagent, which is what? Either chromic acid or sodium chromate. It's actually important if it's the salt or if it's the acid, because those are two different things. I just wrote CrO3. That's not good. Go away, B. All right. Okay. DMP or PCC. The one that I want to write down is sodium dichromate, sulfuric acid, and water. Can I just write Jones, you think, or do I have to write low-key? I just want to write Jones. I prefer it that way. Like, in the real world, we're not going to need to remember this. We're just going to, like, look it up in a book. But the fact that you know that, hey, there's this combo of things that I can use to take this functional group to this functional group, I feel like that is the essence of what's important. Remembering that it's sodium dichromate, it's like, is that important? I don't know. Okay, so yeah, so secondary alcohol to a ketone. This Swern, isn't it? It's PCC. Almost any common. Okay, so if that's the case, then I'm just gonna use PCC. So secondary all to OIC is PCC. Yeah, no oxidation on tertiaries. Okay, so there's not. Okay, now reduction. This arrow is formatted weird. There's not a negative charge on there. So sodium borohydride will take an aldehyde to a primary alcohol, and so will LAH will do everything. And the only thing to remember is that sodium borohydride cannot reduce esters and carboxylic acids. That's the main thing. So you got to use LAH. Got it. Okay, that's actually pretty nice. Okay, so I gotta pack up. I'll probably have, hopefully, like 2 more hours to study to do alcohol problems later today. No mic and no overhead though. So just, me not even talking, just doing them. That was fun, man. I really like this subject.